Hello, my name is Thomas Mueller. I'm a product manager in the AFM business at Bruker. I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation is titled Beating the Diffraction Limit by 1,000 Times, an introduction to nanoscale IR imaging on Bruker AFMs with applications in graphene. It's presented by Greg Andreev. Before I introduce Greg, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We'll accumulate these questions through the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session, and in those cases we'll be sure to follow up with email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate it if you take the time to complete this, as it helps us pick the topics that are most important to you and to generally make the series better. So let's get started. Let me introduce our presenter, Dr. Greg Andreev. Greg is an applications development scientist and technical lead for near-field optics in the AFM unit of Bruker's nanosurfaces business. He received his PhD in physics from the University of California at San Diego at the end of 2011, but has worked with near-field optics for more than 8 years. During his PhD work, Greg constructed the first cryo-SNOM, a near-field imaging microscope which operates at liquid helium temperatures. He obtained the first SNOM images of nanoplasmons in graphene. He also showed the ability for SNOM to distinguish ultra-thin silicon oxides with nanometer precision. Dr. Andreev has co-authored over a dozen publications and is the primary inventor of several patent-pending technologies in near-field optics. So let me now turn it over to Greg for his talk titled Beating the Diffraction Limit by 1,000 Times, an introduction to nanoscale IR imaging on Bruker AFMs with applications in graphene.
Thank you, Thomas, and thank you all for attending this webinar. I'm really excited to present our results and introduce this exciting new technique. So let me get started with the outline of my talk. First I will introduce infrared nano imaging, just the basic physics and how it works. And then in the second part of the talk, I will go into some results contributed by our customers, some very exciting new data. Actually, the majority of the data in this talk is unpublished, and that's very new. And also show some results from us, from Bruker Nano. I'll show some very interesting nanoscale infrared imaging, and I'll show what we think are the fastest images yet of a nanoplasmon in graphene. So let's go into the introduction to infrared nanoimaging by starting to discuss infrared spectroscopy. So why do people use infrared spectroscopy? Well, the main reason is that it allows chemical identification. On the left side of the slide, you will see an example of an infrared spectrum where I point out several key features with the arrows. And this infrared spectrum can be used as a fingerprint for identifying materials. So on the right side, I have shown the molecule, the chemical compound that the spectrum corresponds to, and the molecular resonances that are responsible for the features in the spectrum. So the key takeaway is that the absorption resonances of a compound provide a unique infrared fingerprint. So this is a very valuable tool for characterizing and identifying materials. Now what about performing such measurements at the nanoscale? So on the next slide, I show some examples of infrared SNOM. I will explain what SNOM is in a few slides, but it's basically a method for performing nanoimaging. And I will show some examples of nanoscale infrared measurements on this slide. So as a first example, we can consider the work of Marcus Raschke in 2005 on block copolymers, where he showed some very impressive resolution down to 8 nanometers of individual polymers in this compound. We can also consider the work of Andy Huber in 2008 on semiconductors, where he and others performed some very impressive imaging of a single transistor, not only at infrared but also at terahertz frequencies. And there they also showed some very impressive resolution and the ability to discriminate various charge densities of the compound. There's also some biological applications of infrared nano imaging. For instance, Marcus Brem in 2006 showed that it's possible to image a single tobacco mosaic virus at different frequencies, and he observed some spectral contrast consistent with the presence of organic material inside the virus, as you would expect. And I have also performed some measurements which have very nice resolution as well. For instance, I measured a human tooth dentin where I was able to achieve better than 10 nanometers resolution, and this was in 2011. So these are all examples of infrared nano imaging that have been performed by researchers, and what all of these images have in common is that they are much smaller than the typical spot size that you would achieve in an infrared microscope. So I put here a 2-micron spot, but actually the spot is going to depend on the wavelengths that you're using in your infrared microscope. So it can be as big as 10 microns. So I mentioned repeatedly that these images are achieving resolution as low as 10 nanometers, and that would be over 1,000 times smaller if you were considering a 10-micron spot, if you were considering wavelengths as large as 10 microns, which is what you might use in an infrared microscope. So just to give you some idea of what a 1,000 times improvement of resolution is, looks like, I'd like to illustrate that on the next slide. So for instance, if you take a look at the image of the soccer field on the left, and you pretend like this is your infrared image, well, the power of infrared spectroscopy will allow you to identify some of the features of the soccer field. You can figure out what's grass, where the ball is, and which part of it is the paint. But the resolution is not that great. So if you were able to zoom in by about 1,000 times, here's what it would look like. You would be able to see the individual blades of grass. You would see the soil compound on the ball, and so on. So I'm just using this to illustrate the magnitude of resolution improvement that is possible with infrared nano imaging. So now I would like to talk about how we can bridge this gap and the limitations that we face. So to make this transition, we primarily need to talk about how we can beat the diffraction limit, which limits the resolution of the far field IR image. So let's discuss that. So what limits the resolution in far field optics? So let's consider a far field imaging system, which I show on the left of this slide. You can see that there are plane waves coming in to a lens and focusing on a sample. And there are two objects that you would like to resolve on the sample that are separated by some distance d. So what's going to limit your resolution is the spatial frequency that you can achieve with your illumination source. It's easier to see that if you consider the momentum of your illumination, which I show now in the middle of the slide. So if you consider the spatial frequency that you can achieve with your the outermost ray, then the largest spatial frequency in plane is going to be determined by this K parallel. And that's basically determined by the largest angle that the lens can bend the light. So the main point here is that we're sampling the object using plane waves that have an effective wavelength that's 2 pi over K parallel. from the dispersion relationship for light, you can see that the maximum K parallel that you can achieve is going to be 2 pi sine theta over lambda. Now, that's the highest spatial frequency that you can use to sample your sample surface. So the smallest separation distance d that you can have between the two objects you're trying to resolve is going to be limited by this largest spatial frequency that you can achieve. It's basically a consequence of Nyquist's theorem. You need half a cycle to sample. So the main takeaway is that far-field optics limits the infrared resolution to a wavelength or several microns. Now, what is the scenario for near-field optics? Okay, so let's consider that on the next slide. The resolution limit in near-field optics is a little bit different. So I start this discussion by showing a model near-field imaging system on the left side of the slide here, where I just have a point source that's a distance a above a sample with two objects that I'm again trying to resolve. And the two objects are again separated by some distance d. What's different now is that my point source that I'm going to use to look at these two objects is brought within a wavelength of these two objects. Actually, the distance a is much smaller than lambda. And because of this, we now have access to some additional spatial frequencies that we didn't have access to before when we were using plane waves. Because plane waves have to travel a long distance, they do not contain any evanescent waves. But in the near field, you do have access to these waves. For instance, K perpendicular can now be imaginary, which allows us to make K parallel much greater than 2 pi over lambda, which was the limitation for far-field optics in the previous slide. So now if we make that approximation, we can basically set K perpendicular equal to I K parallel. Now again, in the momentum space, you can imagine that this point source has all kinds of plane waves that it can emit of all kinds of spatial frequencies that satisfy this dispersion relation. You have the choice of many possible plane wave spatial frequencies. But the only ones that are going to actually interact with your sample are the ones that don't decay by the time they reach the sample. So if you choose a spatial frequency that's too high, that wave is going to decay before it can reach your sample. That's what I'm illustrating with these two waves that have, one is a slightly larger spatial frequency, that would be this wave, and this is a lower spatial frequency. You can see that this lower spatial frequency wave takes longer to decay. So it can be used to sample these two objects. This larger spatial frequency wave can also be used, but it's decaying much quicker. If you keep increasing the spatial frequency, eventually that wave will not reach the surface. So that's the resolution limitation in near-field imaging. So here, the maximum spatial frequency parallel to the sample surface is roughly 2 pi over a. So the minimum separation of two objects that you can resolve is about a over 2. So for near-field optics, resolution is only limited by the distance of your sample to the source. The wavelength does not matter. So let's now talk about how we can actually implement such a model near-field imaging system experimentally. So I would like for you to focus your attention just for a second on the red circle, because I'm going to mention that on the next slide. So now let's consider the technique of scattering, scanning, near-field optical microscopy. So in this technique, we basically implement this model near-field imaging system that I showed before using an AFM tip. So what you can see on this slide is that you have incident light coming in. It polarizes a metallic tip, and it creates a dipole at the end of the tip. Now, this dipole is going to be following the electric field of the incident light because this is a conductor. So this dipole is going to switch this plus-minus. It's going to switch plus-minus at the frequency of the incident light. So this is an infrared point source, just like I was talking about on the previous slide. This is a point source of evanescent waves. So if you bring this point source very, very close to your sample, you will now be able to image your sample with these evanescent waves at spatial frequencies that are basically on the order of the separation distance of this dipole to the sample. Now, because the center of the dipole is inside the tip, the closest you can get is about the tip radius. But that's still pretty good because the tip radius can be made as small as 10 nanometers. So you can get within 10 nanometers of the sample surface, and that gives you access to about 10 nanometers over 2, so about 5 nanometers of resolution, potentially. And the reason that this point source is created by the incident light hitting the tip is due to the lightning rod principle. If you have a very sharp object and you apply an electric field to it, you will concentrate some charges and you will polarize that object so that it will have a large charge density at the end, at the sharpest point. So, so the other key aspect of this technique is that you have to detect this. You have created the evanescent waves, but you still have to detect them somehow. And the way that you do that is by monitoring the scattered light of this AFM tip. The scattered light will be able to transfer the interaction of these evanescent waves with the sample into the far field. So you're transferring near field information to the far field. If the sample causes a change in the tip dipole, it will affect the overall scattered light by the entire tip. And the key takeaway here is that the tip radius is what's going to determine our infrared resolution now. It's not going to be the wavelength of the incident light. The wavelength of the incident light can be 10 microns, 2 microns, 20 microns. As long as your tip is about 10 nanometers, you will achieve 10 nanometers resolution because of the lightning rod principle and the evanescent waves that you have access to. So what role does the sample play in all of this? Let's briefly discuss that. So one interesting thing about SNOM is that it works equally well for 3D and 2D materials, and I will just try to explain that in this slide as well. So the effect of the sample on on the evanescent waves that are produced by the tip is that the sample surface will reflect these waves, and these waves will then drive more charges to the tip, or actually they may destructively interfere and actually cause the tip to have a smaller polarization. So I summarized that in 3 different cases on the right. So for instance, if the sample is insulating, then it will reflect a little bit less of the evanescent waves, as I indicated by smaller arrows. And then the tip dipole is basically remains the same. The sample is conducting, you get a little bit more. And if it's a resonant material, if it's a resonant sample directly underneath the tip, then your reflection can be potentially higher than the conducting case. And you will drive a lot more charges to the dipole. Now there's a little subtlety here, is that a resonant material can actually cause destructive interference. It can reflect light in such a way that the phase is different than the phase of the driving light, the light that drives the dipole in the tip. So you can actually have a scenario where you have a resonant material, a very resonant material actually has a smaller tip dipole. So basically, as you go from left to right, you have larger reflection, and that is how you're going to get information about the sample. Now really quickly, let's go over the 2-dimensional case, because here you do not have an image dipole in the sample that you can think about, but you can still think about the reflection of the sample surface. So all of the same arguments apply about reflection. As long as you can calculate the reflection coefficient of your 2D surface, you will get the same sort of effect on the tip dipole. And for a 2D material, I break it up into basically two categories, non-resonant and resonant. And by resonant, I'm talking about primarily plasmon resonances, such as I will show later in graphene. So if you have a plasmon resonance, you'll have a much larger reflection of evanescent waves back to the tip. And you will cause a much larger tip dipole, and therefore you will have a larger amount of scattered light that you can detect in the far field. So that summarizes the effect of the sample on the tip dipole. And now I'll talk about the experimental implementation of this scattering SNOM technique. So on slide number 11, I'm showing the very, very basic optical layout of a scattering SNOM system. So the basic elements in this setup are an infrared source, which is typically a laser. We like to use quantum cascade lasers, but researchers in the past have used CO2 lasers, and you can use many different types of lasers. You can use broadband laser sources as well. So you can have, so basically you will shine this infrared source onto the tip, and you will focus that light with this PM, which is a parabolic mirror. And using that same mirror, you will collect that light. And the scattered light from the tip can be divided into two parts, the near field term and the background term. The near field term is what you want. The background is what you don't want. And I'll explain on the next slide what the difference is in detecting those two. And the other key aspect of this optical scheme is that you also have a reference path. You have an electric field component that travels, that does not go to the sample. It bounces off this MM, which is the moving mirror, and then goes to the detector. And at the detector, all three of these electric fields are combined and to create the voltage on the detector. So in order to get to the information provided by the evanescent waves, we have to get to the near field sensitive contribution to this detector voltage. And to do that, we have to get rid of all possible background terms, which are going to be much greater than the near field term. So how do we do that? So we basically have to expand this detector voltage algebraically to see what we need to do. So if you expand that out, you see that there are 6 terms, and you somehow need to get information about E near field. And the best way to do that would be with this first term that I've highlighted, this E reference times E near field term. All of the other terms have problems. They either contain the background term, which you can't control and you don't really care about, or they're too small. For instance, E near field squared will be too small. So one of the ways that you can isolate this desired term is by making the reference field really large. So you can have a much larger E ref than E background. And then the other way that you can isolate this term, you use both of these together. The other way that you can isolate it is by employing tapping mode, for instance. So if you oscillate the tip, you're oscillating the separation distance between your point source and the sample surface. And therefore, you can reach a separation distance where you don't have any evanescent waves, any significant evanescent wave contribution to the scattered light of the tip. So you're basically modulating the E near field term off and on as you move the tip up and down. And that gives you a valuable way to discriminate, a valuable method for discriminating the E near field term from all of these other terms. So using those two tricks, a large reference field and oscillation of the tip, you can basically isolate this desired term from all of these other terms. And that's how experimentally people measure the near field term in scattering SNOM. And they actually can measure the amplitude and phase of this entire complex valued near field. And this near field term contains information about the nanoscale properties of the sample. Okay, so now let's consider some SNOM results from our customers and how they have implemented SNOM on some various Bruker AFM platforms. So the first result that I would like to show, well, this is actually a setup at the University of Colorado at Boulder. This is Professor Rashke's lab. And this is what a scattering SNOM experiment looks like. You can recognize immediately some of the elements that I showed in the schematic on the previous slides. For instance, here is the infrared beam splitter. Over here you have a parabolic mirror which will focus the IR light on the tip. I have removed the head here for greater visibility, but this is where the tip would be. And you also have the second path, and this is your reference path. These are some attenuators. But basically, this light just goes straight here and then bounces off of this piezo-actuated mirror. And then the light is recombined at the MCT-IR detector. So it's a pretty simple setup. And the method of scattering SNOM has also been implemented at the advanced flight source at the IR beamline 5.4. And there they performed, they used basically an identical optical layout as the one I just showed. And they performed broadband nanospectroscopy of SiO2. And they obtained some very interesting results. These are preliminary results. They're not yet published, but they're already showing some very, very clear contrast between the SiO2 region and the silicon region. And the contrast is visible over nanoscale distances. So these are very promising results, and they may lead to some very exciting research applications. And another very exciting result is from the University of Toronto, Professor Gilbert Walker's lab, where they performed the first spectroscopic nanoimaging of boron nitride nanotubes. I showed their Bruker multimode setup on the left here, and I showed two representative images of boron nitride nanotubes. So this is an example of the type of infrared image that they can obtain. It's clearly showing some very interesting inhomogeneities inside of these nanotubes. There's a little bit of a hot spot on the end. And these are all very interesting topics for research. And they also performed some very interesting spectroscopy at different points along the nanotubes, and they saw drastically different spectra. For instance, location A appears to be much different than location E, indicating that there may be some sort of there may be some sort of effect going on here, which is greatly shifting this resonance from 1380 to 1420 perhaps. And all of these effects are not very easily observed in infrared spectroscopy. As you can see, the FTR spectrum is sort of very broad and it only has one hump. So these are very exciting results, and I invite you to read about them in greater detail in Gilbert Walker's publications. So these are some examples of what our customers are doing with our AFMs in the SNOM application area. So now let's show some SNOM results from Bruker Nano on a 2D material, graphene. So in order to introduce graphene, I should first introduce the people that discovered graphene. Andreev and Konstantin Novoselov discovered graphene in 2010, or they received the Nobel Prize for discovering graphene in 2010. And it was a very exciting material because it's the first example of a two-dimensional material. And actually, one of the primary tools that they used to find graphene was a Bruker AFM. So it became basically a workhorse instrument for identifying how many layers of graphene they were observing. And graphene as a material is very exciting because it has a plethora of interesting properties, unique properties. So it's like one layer in graphite, but it's completely two-dimensional, and that gives it some of these interesting properties. For instance, it's the strongest material ever measured. It has the highest intrinsic mobility, over 100 times silicon. So all of these properties make it a very exciting material for many applications and an exciting topic of research. So that's one of the reasons that I would like to show some exciting images on this 2D material. So let's consider the infrared spectrum of graphene. Now, the infrared spectrum of graphene is very interesting because it basically reveals all of the primary physics of graphene. So it reveals two regimes. So on the right, we have the universal conductivity regime, and on the left of this 2E Fermi feature, we have the Drude conductivity regime. So with a single infrared spectrum like this, you can get information. Oh, whoops. Sorry about that. With a single infrared spectrum, you can get information about all of these properties, such as the carrier density, which you can extract from this E Fermi value. You can get information about defects and substrate effects from gamma. And gamma is going to manifest itself as basically the width of this transition that I'm showing here. And by taking these spectra, you can really perform some accurate characterization of graphene samples, which is non-destructive and relatively easy to do. Now, on the next slide, I would like to show how near-field infrared spectroscopy can also be used to characterize graphene in much the same way. So I also calculated a spectrum that you would get using near-field spectroscopy. Now, the difference is that this spectrum would be using infrared light of a much larger spatial frequency, because now our point source is really close to the graphene. We have access to these huge spatial frequencies, these huge momenta. Because of that, we're able to excite plasmons. And that's what gives rise to this additional feature that's not seen in the far-field spectrum. For the far-field spectrum, you have K parallel is essentially 0. So you're not able to excite the surface plasmon. But for a near-field spectrum, if the momentum is sufficient enough, you can see something like this huge hump that I'm showing in this green spectrum. And but all the other features would still be there. So you'd still be able to discern information about, to discern the value of E Fermi. You'd still be able to figure out gamma, because you still have this transition into the universal conductivity regime that occurs at basically the same frequency. So let's look at some experimental results first in the universal conductivity regime. So we set our IR frequency to about 1730 wave numbers. And this should fall in the universal conductivity regime, provided our Fermi energy is not too high. And we can measure that using the method of KPFM, which I will show on the subsequent slide. So before I go into that, let me mention the Bruker AFMs that are used to obtain some of these images. These Bruker solutions for graphene research are capable of performing co-localized Raman measurements. You can perform TERS with the catalyst iris and the Inogo iris. You can also perform peak force KPFM on the ICON system, QNM, and now it's possible to perform SNOM as well. So let's show some data for a graphene sample. So this is a graphene sample that has a very interesting structure. It has 1, 2, 3, 4 layers, all sequentially arranged in a very small region, which makes it very attractive for all kinds of investigation using our instruments. So, of course, in the top left, I show some AFM height data, which is going to confirm that we are stepping in exactly 1 layer steps. But I also show this G-band Raman data, which allows us to confirm using the G-band frequencies that we obtained how many layers we have. We also perform D-band Raman imaging, which gives us a sense of defects, and it also allows us to confirm that we actually have 1 layer. We also performed peak force KPFM on the same region, and from that experiment we're able to extract an estimate or an upper limit for the E Fermi of the single layer region. And then of course we have our first scattering SNOM results on this sample, which I show in this last image here, and they were obtained in the universal conductivity regime. And images such as these allow us to get information about graphene's optical conductivity. And with these types of images, we can count the number of layers. We can also get an estimate for the Fermi energy. And as I will show in a few slides, we can also study plasmonics in graphene. So let's look at this image in a little bit more detail. So if we draw a line profile through this image, we see that we have a very clear contrast between SiO2, the first layer, second, and third, and fourth layer. There's a monotonic increase in signal as we go from 1 to 4, and we also see that this is very clear contrast. It's not a faint signal at all. It's very clear. And what's surprising here is that the first layer signal is a little bit lower than the SiO2. But let's first consider the things that we actually did expect. So what we expected is that we would have some contrast consistent with an increasing universal conductivity. And that is what this image basically confirms. We see that the conductivity of the 4-layer graphene is monotonically higher than the conductivity of 3, 2, and 1, and so on. And this applies if we're in the universal conductivity regime, which we know we are because the frequency we chose, 1730 wave numbers, should be much higher than twice the E Fermi. And E Fermi was estimated using KPFM. And I also would like to comment that these images are very reproducible, and this can potentially be used for layer counting, as long as you're sure that you're in the universal conductivity regime. And the unexpected aspect of this image is that they're twofold. So basically, the first layer is lower than the SiO2. That was an unexpected result. And there was also this huge jump from the 3-layer to the 4-layer, which we also did not expect. And I made a theoretical prediction. I calculated the expected spectrum, and I indicate the frequency that we used to perform our measurement. And as you see from the theoretical prediction, the 1-layer signal should have been higher than the SiO2. And the transition from the 3-layer to the 4-layer should have also been basically in line with the other transitions. That is not what we observed, however. And this theoretical prediction was made using the random phase approximation for graphene. So there may be some additional elements that need to be introduced into this model in order to account for these experimental results that we're getting. So we can also use this image to characterize the defects in graphene. So if we look at the D-band Raman image that I showed previously, and we zoom in on that region, we can see some hints of a very similar type of defect in the IR image. Now, it's sort of hard to see, but if you concentrate on the region that lights up a little bit in the D-band Raman image, then you can see that it's a little bit darker than the rest of the graphene, of the single-layer graphene region. So if we perform some statistics on that, we can actually show that the signal from that region is lower, indicating a lower amount of conductivity, which is what you would expect if you had a larger amount of defects there. And we can get to the origin of these defects by performing some nanomechanical measurements as well on the same region. So I show that on the next slide, and here the combination of nanomechanical measurements allows us to see some hints of wrinkles, which indicates that this portion of the single-layer graphene may not be attached to the surface as well as the rest of it, or perhaps there's some deformation in this surface. And if we now perform some statistics on the IR SNOM images for that region, we see that taking the average signal over the region that seems to light up in the D-band Raman image, we see a clear difference. We see roughly a 2% difference. So it's an easily detectable 2% contrast that is caused by defects in this outer portion of the single-layer graphene. And those defects are likely connected to the wrinkles that we observed with the nanomechanical measurements. So that's the type of information that one can learn about graphene in the universal conductivity regime. So what about the plasmonic regime? Well, let's put our IR frequency as low as we can go, and we used a frequency of 870 wave numbers, and there we are able to investigate graphene plasmonics. So the type of image that you get if you zoom in on the corner of the single-layer graphene sample is shown here. So this is an image at 870 wave numbers, and you see a clear feature that is related to the interference of the plasmon wave and the tip dipole. So what's happening in this image to create this pattern is that the tip is launching a plasmon wave. It reflects off of the interface, comes back to the tip, and either constructively or destructively interferes with the tip dipole. And then that affects your scattered light that you detect in far field. So, oops. Sorry about that. So what this image shows is that the plasmon is clearly observable, and the length scale of this plasmon is very small. It's basically around 140 nanometers. And we can get a better sense for that if we consider some line profiles through that. So I show that on the next slide. So on this slide, I'm actually going to show two things. I'm going to show these line profiles, but I'm also going to show the effect of very fast scanning. But let's first consider the line profiles. In the line profiles, you can see that the spacing between the individual maxima in the graphene plasmon is about 140 nanometers. But also, what's interesting here is that we repeated the same image at much higher scan rates. For instance, the middle image here is at 4 hertz, and then the next image is at 10 hertz. And we saw that we do not lose too much spatial resolution as we increase the scan rate. So This 10 hertz image is obtained in just 60 seconds. And we did not have a significant loss of spatial resolution. And we believe that this is probably the fastest image of a nanoplasmon in graphene obtained to date. So the SNOM on a Bruker AFM is fast without any loss in spatial resolution, as indicated by these images. So as a final result that we obtain on graphene, I would like to remind you of the previous slide that I showed about the point source of a near-field imaging system creating large spatial frequencies. Now, what if you have a dull tip? In theory, that should have a point source that's removed further from the sample surface. Therefore, you will not have access to the large spatial frequencies that you need. And I performed such an experiment, and I show these results on the next slide. As you can see on the left image, the dull tip produced a very dull plasmon that is not easily discernible. And the right image has a fresh tip, and the plasmon is clearly visible. So this indicates that this picture of large spatial frequencies being available in a near-field imaging system is accurate. And that these large in-plane momenta are a necessity for plasmonics. So with that, I would like to conclude my talk and just summarize that near-field imaging with SNOM is a powerful and unique tool. It has some remarkable sensitivity, allows access to nanoplasmonics, and I would also like to say that we have some new results. We have the first nanoscale IR images in the universal conductivity regime, and we obtained the fastest images yet of a nanoplasmon. Thank you for your attention.
Okay, thank you, Greg. This is Thomas again. I see we do have a number of questions. However, I also noticed the last few slides we stopped sharing. We're going to quickly fix that and have a quick look again at the last few slides. Just a second.
Okay, sorry, it appears that my sharing somehow had a glitch, and we actually paused the presentation at this point. Let me just walk you guys through this really quick. So basically here, I'm showing the graphene plasmon image at 870 wave numbers. And I already mentioned that the origin of the waves shown in this image is due to the plasmonic waves being launched by the tip and reflecting back to the tip. But on the next slide, I show 3 sets of images that are obtained at different scan rates. And these images demonstrate that you do not have a loss of spatial resolution. They also allow us to extract the length scale for the graphene plasmon. We do not lose this ability if we scan fast. We can still determine the length scale. And I just mentioned here that the 10 hertz image is obtained in just about 60 seconds, and we don't have significant loss of spatial resolution. And I think this is a very nice thing about Bruker AFMs, is that we can perform this type of imaging very quickly without losing the resolution. And now for the last slide, I just want to show the effect of the tip radius and how that's connected to the spatial frequencies that you generate in this graphene surface. So on the left, you see an image taken with a dull tip which is going to correspond to a low spatial momentum, a low spatial frequency. And on the right, I show a fresh tip image, which has a large spatial momentum. So the fresh tip image is clearly showing the graphene plasmon, whereas the dull tip image looks very blurry. And that's because it's simply not able to launch these waves. It does not have the necessary spatial frequency. And now I'd like to show the conclusion slide. The near-field imaging with SNOM is a powerful and unique method. And I hope you guys find the new results that we showed here interesting and and possibly a topic for further research. And thank you guys for your attention.
Okay, yeah, thank you everybody also from my side for your attention. So now let's get to the question. I see we have a number of questions. We'll go through a number of them, and as we said, we'll follow up with email on the remaining ones. I see a question that was asked, that was brought early on about, Greg, what do you mean by a resonant material? Can you briefly refer back to that?
Sure. So resonant material is a material that has absorption at the infrared frequency that you're using. So one example is a molecular resonance. So the same sort of resonance leads to absorption dips in an infrared spectrum, such as the one I showed at the very beginning of the presentation. So if you were to tune to one of those absorption lines, you would be near the molecular resonance of that material. Another type of resonance is a plasmonic resonance. So here you have charge density waves on the surface of the material that you can excite. So those are the two types of resonances that I'm referring to.
There's possibly a related question, somewhat related, on the background terms you introduced with the equations. Does the sample itself introduce additional background? Or is that already captured in when you talk about the resonances?
So is the sample itself delivering some background? Yes, that is true. The sample also scatters some background light, which you do not want to measure. And you isolate the near-field light from this background light by looking at the parts of your detector voltage which are modulating at higher harmonics of the tip frequency. That is one way to isolate the near field from the background. The background will not modulate at higher harmonics. It's not really affected by the tip sample separation at the nanoscale, whereas the evanescent waves are. So that's one way you can distinguish the two.
Next, a question on the optical alignment. Do you want to make a comment on the optical alignment, what's involved in setting up this kind of experiment?
Sure. Optical alignment basically involves using a visible laser that's been aligned with the infrared laser, so they follow the same path. And if you have a parabolic mirror, you simply shine your visible laser onto the tip, and then you start looking for your infrared signals. And when you bring the tip into contact, you expect there to be a large near-field signal, and then when the tip is out of contact, you expect that signal to go away. So that's the main characteristic that you use in order to isolate the near-field contribution to the voltage. But in general, it's a pretty straightforward alignment, which is basically helped greatly by the presence of a visible laser.
The question on resolution in terms of frequency resolution, spectral resolution? Okay,
yeah, that's a good question. The frequency resolution, if you're using a laser source, is only limited by the line width of your laser and how much you can tune it. So if you have a monochromatic source, then you're obtaining signals only at that frequency. The tip does not add any additional frequencies to the light that you're using. So For instance, with quantum cascade lasers that are offered by daylight solutions, you can achieve very accurate settings of the IR frequency, I believe down to 0.01 wave numbers. So that can be potentially your spectral resolution limit. If you're using a broadband source, such as a broadband like a DFG type source, then your resolution will be limited by how far you move your scanning mirror to perform the FTIR part of the measurement. So the further you're scanning your mirror, the better will be your resolution.
You showed, next question, you showed one maximum in the plasmonic range of the spectrum. Should there be one or should there be several?
Yeah, so I didn't mention that this is a this was calculated for suspended graphene. I just wanted to keep things simple, but in general, you're right. There will be another peak due to the substrate. So I used a very simple model. So in my calculations, I only have one maximum.
And then there are questions on the spectroscopy aspects, like what frequency range would be available in mid-IR?
Okay, the frequency range in mid-IR is again sort of limited by the laser sources which are available. But for instance, you can go to the website of Daylight Solutions and take a look at some of the QCLs that they offer, and there's already quite a big range that's commercially available. I think it's possible to cover 3 to 12 microns already, and I think that's there's continuous improvements in that industry.
Thanks. Yeah, there was another question whether this is available with the Innova or Multimode 8. So let me answer that quickly. Basically, both the Multimode 8 platform as well as the Innova. And please contact us for more details. Another question: do you need special tips to do this?
No, the tips do not need to be particularly special, except that they should be metallic. They should have a metallic coating, because one aspect of this whole technique that I didn't really focus on is that you need an antenna. You need to create an infrared antenna. So if you just have like a little nanoparticle that's conducting on the end of the tip, that's not enough. You need to drive currents up and down the entire tip. So all that's needed is a conducting tip and preferably a tip that operates in tapping mode or has a high resonant frequency. The higher the better. And it should have a visible tip apex that also helps with collecting more signal.
Do you obtain a spectrum at each pixel, or do you typically image at a discrete wavelength when you do images?
Yeah, that's a good question. You can perform both. So usually we're more interested in the imaging because the imaging gives us the nanoscale information. But we can, and people have done this, we can go to a single location, stay there, and change the frequency of the laser and record the signals. That's another way of obtaining some spectroscopic information. But you can also just take images very quickly at successive frequencies and build up a spectrum that way as well.
A question here about semiconducting materials. Can you obtain information about them?
Yeah, you can. With semiconducting materials, if you choose a very long wavelength, like if you choose like 11.5 or 12 micron wavelength, you can actually access the plasmon resonance of a semiconductor. You can actually look at the Drude contribution to the infrared reflection, and you can get some information about the charge density. You see contrasts between a charge density of, say, 10 to the 18 to 10 to the 19. You can see those contrasts very clearly, And that's shown in the work by Andy Huber that I referred to earlier. You can get a lot more information about that in his papers.
A quick question on graphene. Why is it important to count the layers in graphene?
Yeah, so counting the layers in graphene is interesting because, well, it's kind of an interesting benchmark for optics. It's not very easy to have an optical technique that can resolve, something below a nanometer. So that's already quite interesting. But also, there's some difficulty with quantifying whether the first layer is really single layer or not. So for instance, we know that we have n plus 1, but is n going to be 0 or is n some other number? So we need some way to confirm that we're looking at single layer. And if we have a method that can do that very quickly, then that can potentially be useful as a combination with other methods.
But yeah, I'd add in few layer graphene. If you have a few layers, each individual layer may truly change the properties. So it's important in research. Also in more scalable graphene production, it's hard to make consistent graphene with a consistent number of layers or a low defect density. So I think it's generally always important to know. A question here, is tip heating a problem if you have, say, a low melting material, maybe a polymer that melts relatively low?
Tip heating is usually not a problem because the types of laser powers that we are using are below 1 milliwatt. That's all you really need to get enough signal. That's how much laser power you need going into the interferometer. Yeah, that's ultimately going to be focused on the tip, so it's focused to about a 10 micron spot on the tip, but it does not affect the tip. And I can observe this experimentally by looking at the tapping amplitude of the tip, and if I observe no major changes, then there is no significant tip heating. But as you go to powers that are higher, like if you go above 10 milliwatts or 15 milliwatts, you can start to heat up the tip and, of course, the sample underneath as well. So you need to avoid going to such high laser powers. And luckily, we don't need to do that because the signal to noise is good enough at laser powers that are less than 1 milliwatt.
A quick question on the optical setup. You showed it briefly. Are the IR optics on the same side as the AFM tip or on the opposite side of the sample?
Not sure I completely understand the question.
You showed a parabolic mirror in your setup. Is it situated on the same side of the sample where the tip is, or is it looking at the sample through it from the backside?
Oh, whether it's looking through the sample, like transmission mode?
Exactly. I think that's the question, yeah.
Well, yeah, if that's the question, then no, the parabolic mirror is actually focusing from above. It's not a transmission geometry. Hopefully I understood the question. I'm not sure exactly.
One question on it says here the interference you're showing. Maybe that was about the plasmon, where you're showing sort of does the period relate to the excitation wavelength?
Well, the wavelength is not important. It's the frequency that's important. So the frequency of the infrared light, yes, it does change this interference pattern. You will start to see that you can essentially map out the dispersion curve of the graphene plasmon if you perform these measurements at several frequencies. And there, you will find that at certain frequencies you have no plasmon at all, which is all very consistent with graphene's dispersion curve. And there are some papers on this. You can take a look at some work from Dmitry Basov and Rainer Hillenbrand. They've calculated these sorts of effects.
Okay, thanks. Yeah, we are more than 5 minutes over time, so we have to end now. Don't hesitate to contact us with further questions about this. You see on the final slide Greg's email, or otherwise, please do contact us. We will look at the complete list of questions. We see there are some more, and we'll follow up with you also via email. Again, please take the exit survey that helps us further improve our webinar series, and we hope to see you soon again at one of our future webinars. Thank you. Bye.
Yep. Thank you, everyone.